and we will keep the second lecture of this week, which is I think on Friday or something. We will keep that lecture for discussion of the test, the common test, which happened on Sunday. Okay. Just a minute. Let's begin. So today we'll be talking about the last part of heat transfer, which is radiation. Oh, your test was cancelled. Achha, sorry. So it is postponed to next week. Okay, so you have some more time to prepare. Good. Okay. So anyway, what we are discussing today will not be coming in the test, which is radiation. Okay. Okay, so anyway, as I was saying, we will start with the discussion of radiation, and your syllabus for the test is excluding radiation. Then we will keep the second lecture of this week for discussion of any doubts in the portion of your test, okay, up to conduction. Anyhow, let's begin. So we have been discussing about heat transfer and the first mode of heat transfer, which is conduction, in the last few lectures. So the first mode is conduction, which we just completed. So we saw this was the primary mode for heat transfer in solids. Okay. Because it is heat transfer by the by means of vibrational kinetic energy of molecules. Now the second mode of heat transfer is convection. So this is the primary mode in fluids, which includes liquids and gases. Now we will not be discussing too much about this because it's not in our syllabus. Okay, so in the case of convection, it is heat transfer through the transfer of translational kinetic energy. Translational and rotational of fluid molecules. This process involves the convection currents. Okay. So just briefly understanding what this process is about. Suppose we have a container which has a fluid of some type, like it has water or something, let's say. And then what we are doing is we have a source of heat somewhere at some position. So there is a heat source over here. So what happens is where the heat is directly getting supplied to the liquid molecules through conduction happening through the container walls. Okay, so immediately at that position, the liquid molecules are gaining kinetic energy. Now, liquid molecules have which type of kinetic energy? They have translational and rotational kinetic energy. So they become more active. So they are moving faster compared to the liquid molecules at other positions which are at lower temperatures. So lower temperature means they have less kinetic energy. This is at higher temperature means they have more kinetic energy, average kinetic energy. So it sets up a current within the liquid. So the higher kinetic energy liquid molecules, they start moving towards the positions where the lower kinetic energy ones are there, and the lower ones, they start circulating back towards this, and like this a continuous flow of liquids is set up. So this process is called convection currents. Okay. Now convection currents are highly disordered. So this is movement of fluid molecules from a region of higher kinetic energy, that is higher temperature, to lower kinetic energy. And the resultant transfer of heat. Which is what we basically call convection. So that is what convection currents are. Okay. So this movement of fluid molecules or convection currents. Okay. Convection currents are highly unpredictable. And also disordered. Okay. So therefore, they are studied empirically, that means experimentally, and by simulation. In higher physics, okay, not at our syllabus level. At our syllabus level, we should just have some qualitative information about what is convection currents and what is convection by definition. So this information is enough. This is all we have in our syllabus about convection. Okay. There is no mathematical model or mathematical equations related to convection at our 10+2 syllabus level. Okay. So that brings us to the third mode of heat transfer, which is radiation, and we'll come to that next. Okay, so now let's move on to radiation, the third mode of heat transfer. Now, radiation is different from convection and conduction in the sense that it is a mode of heat transfer via electromagnetic waves. Okay. So as you know, light is also part of electromagnetic waves spectrum. Visible light, okay, UV, infrared, etc. Due to continuous emission slash absorption of photons, which are packets of electromagnetic energy at the atomic scale. That is, atoms are continuously emitting and absorbing photons, and that process of heat transfer is called radiation. Okay. So radiation does not involve a material medium. Okay. Therefore, radiation is the primary mode of heat transfer in space, vacuum. So for example, solar energy, which is heat by radiation, so the transfer of solar energy from the sun to our planet, etc., it happens purely by radiation. So it is not only heat by radiation, but it is radiation purely. There is no other form of heat transfer involved. Okay, so that is the basic concept of radiation. Now let us understand the equations that we can write for radiation. So this is the third and final mode of heat transfer. Okay, so let us look at the terminology involved in radiation. Okay, so the first principle to do with radiation is Stefan's law. Of radiation. It says that any surface okay, at surface temperature capital T in kelvins. So any surface emits heat by electromagnetic radiations such that it has an something called emissive power. I'll explain what emissive power is. Proportional to the absolute temperature to the power 4, where T is the absolute temperature of the surface. So emissive power E, its definition is the energy radiated per unit time per unit surface area. So it is expressed in joules, that is energy, per unit time, that is per second, per unit surface area. So that is per meter square. So joule per second is the same thing as watts meter square, because 1 watt is equal to 1 joule per second. So this is the first thing that we need to know about radiation. Is Stefan's law, sometimes also called Stefan-Boltzmann law. So this is what is called an empirical law. That means it is not derived theoretically, but from experiment. So just make a note of this so far. Then I'll explain the constant of proportionality in this equation. let us understand further about Stephen's law by understanding the constant of proportionality. Okay. So now this proportionality is solved further by the product of two constants, where sigma is Stephen's constant of radiation. Sometimes it is also called Stephen Boltzmann constant. Okay. Which is okay, which is a universal constant, which means that it is independent of anything else. Like the material of the surface or its environment, okay, or temperature, etc. So Stephen's constant is again determined experimentally. It is given by 5.84 into 10 raised power minus 8 watts per meter square Kelvin to the power 4. So again, this is the experimentally determined value. You don't have to memorize the value. It will be given to you in the question paper at the NEET level. Okay, but should have an idea about the kind of value it has. In many questions, we will approximate it as 6 into 10 raised power minus 8. So it is just correction here. It is 5.67, not 8.4. It is 5.67 into 10 raised power minus 8. Okay, now the other term here, small e. This is called emissivity. And it is a material property. It means it depends on the material of the surface. Okay. Now, emissivity is dimensionless. Is a dimensionless constant, and its value is just a fraction between 0 and 1. Now, the emissivity value is equal to unity or 1 for a material called a perfect black body. Which is, you can think of it like the perfect radiator of heat, because it has maximum emissive power compared to all materials. Now, such a perfect emitter of heat called a black body is, it is a theoretical material. It does not exist in practical physics. In practical physics, we have materials like lamp black and certain forms of copper, certain forms of carbon, which are very, very close to E equal to 1, like 0.998, but nothing has perfect emissivity of E equal to 1. Every known material will have emissivity less than 1. So practically, all known materials have emissivity less than 1. So another way to define emissivity for a material can be defined as the ratio of emissive power with respect to the ratio of emissive power of a black body at a common temperature for a given material and a black body. Okay, so from Stefan Boltzmann law, we also understand that if we have a certain surface which has surface area, say S, surface temperature, capital T, and emissivity of the surface, small e, then the rate of emission, that is heat loss by radiation, or you can also think of it like delta Q by delta T. So dq by dt by emission is given by the formula emissivity into Stefan's universal constant multiplied by surface area into temperature of the surface to the power 4. This is very simple to understand because emissive power was basically the net rate of heat loss by emission per unit surface. Emissive power, the rate of radiation per unit surface area. Okay, and emissive power we had seen was equal to E sigma into T to the power 4 by Stefan's law. So hence, if you multiply the surface area to the emissive power, we get the net rate of heat loss by emission. Okay. Now, the other thing to understand is that any surface also continuously absorbs electromagnetic radiations. So it's a simultaneous process that happens, absorption and emission. If this temperature is capital T, but the environment it is in has what we call surrounding temperature. The surrounding environment has a surrounding temperature of, let's say, T naught in kelvins. Okay. Then there is something called absorptive power, just like we had seen emissive power. Okay. So absorptive power is energy absorbed per unit time per unit surface area. Okay. So it is again in joules per second per meter square or watts per meter square. So this absorptive power is proportional to the temperature of the surrounding to the power 4. Okay. And the constant of proportionality is something called absorptivity, just like emissivity, into the same Stefan's constant, universal Stefan constant, into T naught to the power 4. But small a here is called absorptivity of the material of the surface. So it's a material property. So this process of absorption is continuously taking place simultaneously with the process of emission. But notice that the emissive power depends on the surface temperature, whereas the absorptive power depends on the surrounding temperature. So we will also understand in some time that if the temperature of the surface, capital T, is greater than the temperature of the surrounding, T naught, then the rate of emission will be greater than the rate of absorption. And vice versa. If the temperature of the surrounding is more, then the rate of absorption will exceed the rate of emission. Okay, so next up we will see something very interesting. That is that the value of emissivity E for any material and absorptivity A are identical. Now, this might be surprising because it means to say that if something is comparatively a good emitter of heat, it is also a good absorber of heat. But this is easy to understand, okay, because if the temperature of the surface is equal to the temperature of the surrounding, then the net rate of heat exchange by radiation should be zero because there is thermodynamic equilibrium. Okay. Because the fact that temperature of the body is equal to temperature of the surrounding means that the material or the surface is in thermodynamic equilibrium with the surrounding, with its environment. So therefore, if T is equal to T naught, that means emissive power must be equal to absorptive power. That means E into sigma into T to the power 4 is equal to A into sigma into T naught to the power 4 if T is equal to T naught. Whenever the temperature of the body is equal to the temperature of the surrounding, then its emissive power must be equal to absorptive power. So that means, and that proves that emissivity is equal to absorptivity. Okay. So therefore, a perfect black body material has emissive power equal to absorptive power of unit, whereas all known materials in practical physics have E equal to A less than 1. And also it means that a comparatively good emitter of heat is also a good absorber, and vice versa. So this also shows that a black body is the perfect emitter or absorber. Yeah, Rahil, to answer your question, uh, no material can have emissivity or absorptivity equal to zero because all atoms are continuously always in the process of emission and absorption. Okay. It cannot happen that we have a material surface whose atoms are absolutely not emitting or absorbing a single photon. Okay. So to understand that, actually, you have to get into the quantum mechanics of atomic structure, which is something outside the scope of our syllabus here. But what happens is the electrons in an atom exist in different quantum energy levels, as you know. And by probability, the electrons are continuously making jumps from higher to lower energy states or from lower to higher energy states. So whenever an electron jumps from a higher to lower energy state, it will end up emitting a photon, and vice versa. Whenever it will jump from lower to higher energy state, it is able to do so because it is absorbing a photon from the environment. So this process of transitions of electrons from one energy state to another, by probability, it is always occurring. It cannot happen that a material is there where none of the atoms are undergoing any transition for a period of time. Okay. So that is why the emissivity or absorptivity cannot be equal to zero either. And why it cannot be equal to 1 is more a matter of definition. We define the perfect black body as a material which has the highest value of emissivity or absorptivity equal to 1. And all other materials we define as relative to the theoretical black body. So relative to that perfect emitter or absorber, they have a lesser amount of emissive power or absorptive power. So hope that clears your point, Riley. Okay, good. Okay, so now that we have understood emissive power and absorptive power, we can also understand the net rate of heat exchange by radiation for a given material. Okay. So if we have a situation where the surface temperature is lesser than the surrounding temperature, so if surrounding temperature is greater than the surface temperature, then the surface gains heat energy over time, such that the net rate of heat gain, okay, this quantity, the net rate of heat gain plus dq by dt net will be equal to rate of absorption minus the rate of emission. Okay. So that will be equal to surface area multiplied by absorptive power minus surface area multiplied by emissive power. So that is E sigma into surface area into temperature of the surrounding to the power 4 minus emissivity into sigma into the same surface area but multiplied by temperature of the surface to the power 4, where we understand that T naught is greater than T right now. And also we understand that emissivity is absorptivity. So this becomes the common value of emissivity or absorptivity, whichever we take, into sigma into surface area into T naught to the power 4 minus T to the power 4. So this becomes our net rate of heat absorption. Because it is absorption, we will write the net rate with a positive sign. So this is the net rate of heat gain in joules per second or watts. Okay, now similarly, if we have a situation where temperature of the surface is greater than the temperature of the surrounding, then the surface loses heat over, because the rate of emission is greater than absorption. Okay. And similarly, we'll write a formula for this. So just make a note of this up to this point. Okay, so in this case, the net rate of heat loss we'll write as minus of dq by dt. And that will similarly become E sigma into surface area into capital T to the power 4 minus T naught to the power 4. Okay, so this is a case of net loss. This is a case of net gain. Again, capital S is the surface area. Okay. So ultimately, when we are dealing with numerical problems, Stefan's law, these are the two important formulae. I mean, they are the same formulae. You can see that in one case, T is greater than T naught, and the other case, T naught is greater than T. Okay, so most of the problem solving, numerical problem solving will be direct formula based. So let's look at an example. We just need to know how to substitute the various quantities in this given formula. So suppose we have a solid metallic cube like this. So a solid metallic cube of dimension L by L by L, where L is, let's say, 50 centimeters. Okay. Now the surface is at a temperature of, let's say, 127 in an atmospheric temperature of T naught equal to 27 degrees. Emissivity for the metal is given to us as 0.4 and Stefan's constant is 5.67 into 10 raised by minus 8 watts per meter square Kelvin to the power 4. So you want to find the net rate of heat loss, because we can see temperature of the surface is greater than temperature of the surrounding by radiation. Okay. So this is the type of question you expect at the NEET level, and it's direct formula based. So we can see that the net rate of heat loss, we'll always write with a minus sign, will be equal to the rate of emission minus the rate of absorption. So that is E sigma into surface area into T to the power 4 minus A sigma into surface area into T naught to the power 4. But remember, E is equal to A, equal to 0.4 over here. Okay. So this net rate of heat loss becomes E sigma into surface area into T to the power 4 and minus T naught to the power 4. So emissivity we are given, we'll substitute. Sigma is given, say, Stefan constant. Surface area will become 6 times L square. So 6 into 0.5 square. So 6 into 0.25 in meters square. It is 1.5 meters square. Okay. So this 6L square is the area of the 6 outer faces of the cube. Okay. So that is the only thing in which we have to apply a little bit of geometrical concept. Rest is direct formula based. Okay. Now the other, so this is S. Now the other thing is T must be substituted in kelvins. So it will be substituted as 400 kelvins. And surface temperature similarly, surrounding temperature similarly will be 300 kelvins because it is given to us as 27 degrees. So now substituting all these things in this formula, we have to just calculate. So we can see that the net rate of heat loss will become emissivity, which is given to us in the question as 0.4 into Stefan's constant, okay, into surface area, which we just saw as 1.5 into now this thing 400 to the power 4 minus 300 to the power 4. Okay, so just note down up to here. We'll complete the calculation next. Okay. You can see the calculation is quite easy because you can take 100 to the power 4 common between the two terms inside the bracket. Okay. and 100 to the power 4 is 10 raised power 8, so it will cancel with 10 raised power minus 8 of Stefan's constant. So ultimately this becomes pretty simple to calculate. So this numerical value of net rate of heat loss we'll get will be in joules per second or watts. Okay, people. So yes, let's calculate the value of this. So as you can see, this will be 0.4 into 5.67 into 10 raised power minus 8 into 1.5 into 4 to the power 4 minus 3 to the power 4 into 10 raised power 8. So further, that is 0.4 into 5.67. Just a second. Hello. Yeah. Into 1.5 into 4 to the power 4 is 16 square. So that is 256 minus 3 to the power 4. Similarly, 3 to the power 4 is 9 square. So it's 81. Okay. Into 10 raised power minus 8 plus 8, that will become 0. So ultimately, we are left with this calculation: zero point 0.4 into 5.67 into 1.5 into this will become 25 minus 8, so that is 17. Okay, so this much in watts or joule per second. So this is one type of calculation question that you can get in this chapter at your NEET level. Okay. Let's just complete this calculation now. Yes, so that is 595.35 watts. So this is the net rate of heat loss, which is what we are calculating in the first place. Okay, people, so hope this is clear. Okay, now next thing we will see in radiation is another principle called Newton's law of cooling. So the statement of this principle is that when we have some material which is at a temperature T, which is the surface temperature, in a surrounding temperature of T naught, so if the temperature of the surface is greater than the surrounding temperature such that delta T is very small compared to T naught. Okay. So remember, these temperatures are in kelvins. So for example, if the surrounding temperature is 300 Kelvin, but the surface temperature is 310 Kelvin. So the difference is 10 Kelvin, and that difference is small compared to the surface temperature because, sorry, the surrounding temperature, because this is 10 Kelvin and this is 300 Kelvin. Okay, so if this condition is satisfied, then the rate of cooling, okay, that is the rate at which the temperature drops with respect to time, is directly proportional to delta T, or the rate of cooling is equal to some constant into T minus T naught. This is the statement of Newton's law of cooling. Okay, so this is the rate of temperature drop with respect to time. Okay, and C is a constant. So this is the statement of Newton's law of cooling. So as a simple application, let us say that a body is placed in a surrounding of temperature T naught equal to 300 Kelvin. Okay. Now, if the initial temperature of its surface was T1 equal to, let us say, 315 Kelvin, okay, and the rate of cooling was 0.02 Kelvin per second, then find its rate of cooling when the surface temperature has dropped to T2 equal to 310 let's say 306 Kelvin. Okay, so just note down this formula first of Newton's law of cooling. Then we'll see how to apply this. Okay, so let's work out this question. Yeah, Sarvesh, we've taken negative sign because the temperature is dropping. Na? This is the rate at which the temperature drops. Hence, there is the minus. The minus sign is there because the rate at which the temperature drops. Okay. So anyhow, let's see. Initially, okay, the rate at which the temperature drops will be equal to some constant into T1 minus T0. So we have this, the rate of heat loss is 0.02, sorry, temperature drop, okay, in Kelvin per second. That is equal to this constant into T1, which is 315, minus T0, which is 300. Now, finally, the rate of temperature drop will be the same constant but multiplied by T2 minus T0. So this rate in the second case will be equal to the same constant but into T2 is now 306 minus 300. Okay. So this is our first equation. This is our second equation. If we just divide the two, we can see that the rate in the second case divided by the rate in the first case is equal to 6 divided by 15 or 2 by 5 or 0.4. So the rate in the second case will be 0.02 into 0.4. So that is 0.008 Kelvin per second. So in the second case, the temperature is dropping at the rate of the rate at which the temperature changes is negative because it's a rate of temperature drop. Or what we call cooling when T2 is equal to 306 Kelvin. When the surface temperature is 306. Okay, so hope the calculation is clear, everyone. And Sarvesh, hope you understood the significance of the negative sign. So with this, we will conclude today's session. And next lecture, we will look at some more applications of Newton's law of cooling. And then eventually one or two more final formulae in radiation, something called Wien's displacement law. And we'll also see the connection between Stefan's law of radiation and Newton's law of cooling. And with that, we will complete heat and thermodynamics. Okay. So we are in a position to complete heat and thermodynamics within the next lecture. And the next section of physics we will start after heat and thermodynamics will be fluid mechanics and properties of matter. Okay, so that's it for today's class, people. Wish you all the best.